So we are discussing the small signal stability analysis of multi-meson system. Okay, now it's visible.
Yes, sir, it is visible.
Visible to all. Okay.
Yes, sir.
So we are talking about the small. Already we discussed the small signal stability for a single meson infinite bus, and later on we considered the power system stabilizer into account, and we discussed, and we have uh, ultimately we derived this equation, right? Okay. And now we'll talk about the multi-meson system. So in the case of multi-meson system, as it's an interconnected system, we'll consider generator equations as well as the network equations and the load. So we are talking about the multi-meson system, right? Now we'll see the differential algebraic equations for the power system. First, we'll talk about the differential equations for generators. Already we have derived these differential equations for sub-transient model, right? So, and this is your showing equation already we have derived. Just we have to write that those equations for ng number of generators as it is mentioned here. So in this system we are considering n number of buses and ng number of generators. Okay. So these equations for all the generators. So that is for all the ng number of generators we are writing this equation. Now this is also for differential equation for exciter, and this is for the PSS, power system stabilizer. Now this is the differential equation for the turbine. Then stator algebraic equations already we have derived. These equations are all meant for all the generators, that is ng number of generators. Now we'll see the network equations. So basically the network equations are nothing but the power balance equations. So we can write these equations considering the generators and the loads as well. So first we'll write these equations for the generator buses, then we'll write for the load buses, right? Okay. These are the equations for the generator buses, because when we write the power balance equation, we generally mention PGI PGI minus PDI equal to PI, right? Here you can see here, this is the generation PGI minus PDI, and this is the injection, this part which is represented through the Y bus element. You can see VI, VJ, YIJ. This is the injection, power injection at particular node, at ith node. And this is the generation, and this is the load. So PGI minus PDI minus Pi equal to 0. So this is for the generators. Okay. Similarly for the reactive power as well. Okay. Now network equations for the load buses. The number of load buses we have is from ng plus 1 to n. Okay. And this is the equation for the load buses, which is nothing but PD plus Pi equal to 0. Okay. So that is the differential equations again can be represented as the state space model. Let us write this in the state space form. Let us write xi dot equal to fi xi I di. Xi is not the state variables. Idi is the direct axis currents. Iqi is the quadrature axis current. Theta g is the angle, bus voltage angle at all the generator bus, and Vg is nothing but the voltage magnitude at every generator bus. U is the input variable. Here input variable is nothing but the reference power and the reference voltage and the power, right? And that already have mentioned this. So here we can see the state variables. These are the state variables we considered, and this is for all generator buses. And UI is V reference and P reference. Theta G is the angle of all the generator buses, voltage angle of all the generator buses, and Vg is the voltage magnitude of all the voltage buses, right? Similarly, theta L and VL, they are the voltage angle and the voltage magnitude at the load buses. The starter equations can be written as this. The algebraic equation we can write in this form for all the generator buses. Then for the network power balance equation we can represent through HI or H, and then the network balance equation for load buses can be represented as K. Okay, so then these functions we can represent uh, with a steady state operating condition, and we can linearize these equations because these are all nonlinear equations, nonlinear functions of the variables, different variables, state variables. So we can linearize it using the partial differential method. So these are the equilibrium points. We can see this x is state variable, id is the direct axis current, iq the quadrature axis current, and ui is the input variables. This is for all NG buses. The network voltages and angles, the initial conditions are represented as this. These are the initial conditions for the network parameters for the load bus and the generator bus. Then linearizing the state space around the initial operating condition, and considering these initial conditions, if we linearize these taking the partial derivative, then we'll find, let us take the partial derivative and we can find these equations, right? So let us see it further. So your state variable or your state space model will look like this. This A1 I is the system matrix. That is obviously 14 by 14 because we have 14 state variables. And similarly, B1 is 14 by 2 because we have here delta ID and delta IQ, two variables. Similarly, B2 is 14 by 2 NG, and this is fit for generator bus, and for load bus it will be 0, the matrix of 0 elements. Similarly, for input we have two inputs. One is your delta V reference and delta P reference. So therefore, your W matrix is of the size 14 by 2. So each of the matrix size is given as a subscript to the corresponding matrix. And if the above linearized equation is formulated for all the generators and the equations are put together. So this is for a single generator, only one generator. If we'll consider all the generators simultaneously, we can write the state space model like this, right? We'll see this is the state space model considering all the generators, that is delta x dot equal to A1, which is 14 Ng by 14 Ng, and delta x is 14 Ng by 1 because we have Ng number of generators and each generator is associated with 14 number of state variables. So therefore the dimension will become 14 Ng by 1. And similarly other matrices are written here. You can go through it and you can analyze and you can easily understand this. Okay. So where delta x is, we know it is a state variable combination of all the generators, delta x1 to delta xng. So each of the delta x is consisting of 14 state variables. Like delta x1 is consisting of 14 state variables. Similarly, up to delta xng, right? Similarly, delta u is consisting of ng number of delta u's from delta u1 to delta u-ng. So each of these state variable, each of these input variables are consisting of two variables, that is delta p reference and delta v reference and delta p reference. Similarly, delta idq is consisting of each of the generators idq current up to ng idq current, right? Similarly, just linearizing the algebraic equations, we can find the equations as follows. You can see these equations. If we linearize the algebraic equations, we'll find these equations. You can try this also. Writing the above linearized equations for all the generators together and considering all the algebraic equations, we can write this equation as the linearized model. Similarly, linearizing the h and k equations, it will lead to these equations. This is for the h and this is for the k equation. Okay, so h is associated with all the generators and k is associated with all the load buses. Network equations. Now we can see this is also k equation. So combining together the above equations for the whole system, it can be written as this. It will combine all the state equations and the algebraic equations together. We'll find the combined equation in the form of, so that will give us a state space model. Further, we can reduce this model. How we can reduce? Just by different manipulation, we can reduce it. Just we can see from this last equation, we can eliminate delta theta L and delta VL, which is nothing but d5 inverse d4 into delta theta G delta VG transpose. And let us assume another variable, that is another matrix D6, which is equal to D2 minus D3, D5 inverse D4. And we will substitute this delta theta and delta VL in the second equation and this D6 into the third equation. So now we can have this equation. We'll find the delta IDG and delta theta G and delta VG in terms of the state variables. So this is very important, and we can substitute this further in order to reduce the state space model, right? So now delta x dot can be written as this. Previously we have found this, and from this equation can be further written as this. We'll expand this second term, a third term of the delta x equation, this term, we'll find this delta x dot as a1 delta x plus b1 b2 delta idg delta theta g delta vg plus w delta u. Here we can substitute this equation. If it is substituted here, you can find this equation, that is delta x dot will be equal to a system matrix to delta x plus w delta u. So your A system matrix will become nothing but this matrix, that is A1 minus B1 B2 into C2 D1 C4 D6 inverse C1 C3. This is your system matrix. This gives us the complete system matrix for a multi-mason system, right? So now this equation is in the state space form with the state transition matrix A system, input matrix W, state vector delta x and input vector delta u. So delta x is the dimension of delta x is it is around 14 ng by 1. So the small signal stability of the multi-mason system can now be known by finding the eigenvalues of the state transition matrix A system. This A system is very huge matrix. It is 14 ng by 14 ng. So if your ng is, suppose in a system we have 50 generators, it will become very huge matrix, right? Okay. So therefore, the eigenvalues of this matrix will give us complete stability information. Since the rotor angle of any synchronous machine should be defined with respect to a reference, one state variable corresponding to the rotor angle of the generator, which is taken as reference, becomes redundant. Hence, there will be 1 0 or a slightly positive eigenvalue corresponding to the redundancy of the system. So this is all about the small signal modeling of the multi-mason system. Okay, so we'll stop here. So any question or any Everybody is audible?
Yes, sir.
So, any question or any doubt, or else we'll stop today's class.
So what is this 14 ng? In 14 into ng.
14 there are 14 state variables, and we have
Okay.
ng number of generators.
So
Okay.
that matrix will be 14 times ng. If ng
Yes,
is
14,
suppose
14
we use
times
for
ng, yeah.
140482.
14
Okay.
times ng.
Okay.
Yes. Okay. So this is the model about modeling of the small signal model of the multimeter system. Okay, so thank you all once again. So today we'll discuss small signal stability, whatever remaining portion, and then we'll discuss the transient stability analysis. Okay, so today we'll finish small signal stability analysis. Is it visible, the screen?
No, sir.
Not visible? What happened? Is it visible?
Yes, sir.
Sometime it is closing. Okay, now it's visible, right?
Yes, sir.
Huh? Visible?
Yes.
Okay. So this we have discussed last class. That is the uh, multi-machine system. That is the system matrix how we derived for the multi-machine system. Last class we have seen this. Right. So this is uh, your system matrix. Right. ASIS, and already we derived this last class. And so today we'll discuss the little bit of synchronous resonance. Okay, already we have discussed this in the last class. Today we'll discuss sub-synchronous resonance. Okay. Okay. So what is sub-synchronous resonance? We need to see. So actually, this phenomena observed in 1975 in Mojave, California, where the turbine generator shaft has failed due to torsional oscillation interacting with the subsynchronous oscillations. Please mute your mic. All of you, please mute your mic so that disturbance will not come. Okay. So because of the series compensation, it happens, this subsynchronous resonance. To understand this phenomenon, let there be a single machine connected to an infinite bus. Let us consider a single machine infinite bus system. So where the subtransient voltage E double dash we are considering behind the subtransient reactance, that is X double dash. Okay. And let the effective impedance between the generator terminal and the infinite bus be Re plus JXC. And the system is looking like this. You can see here, this is the generator with E double dash as the subtransient voltage behind X double dash. And XE and RE, they're the effective or uh, the reactance, effective reactance and effective resistance, and XC is the capacitance which is connected as the series compensation. Okay. Now let us analyze this. What happens when the fault occurs in a system? When the fault occurs, there will be a transient in the current with offset, and generally this offset oscillates at a natural frequency. Generally, if the capacitance is not present, there is no natural frequency, so therefore it is called DC offset. Okay, but as soon as the capacitor comes into picture, it has a natural frequency. This fault current, which is decaying in nature, that DC offset is decaying, but it is oscillating at a natural frequency. It is nothing but 1 by L root over LTC. That is, LT is the total inductance and C is the series compensation capacitance. So with certain adjustment, we can write this equation in terms of synchronous frequency, that is omega s under root xc by xt, right? We can write this equation 1 by LTC as this. Okay, everybody knows this. Now I can express Fn, that is the natural frequency, as Fs into Xc by Xt, right? Okay. So Fs is nothing but the synchronous frequency, where Fs is the synchronous frequency and Xt equal to X double dash plus Xc. These oscillations at the frequency Fn, that is the natural frequency, in the starter current of the generator will induce a sleep frequency, that will be Fs minus Fn, that will induce a voltage with having frequency Fs minus Fn in the rotor circuit, okay, and thereby producing the sleep frequency torque. If Fn is a subsynchronous frequency, then since the rotor is rotating at synchronous speed in the steady state, then sleep we can find as Fs minus Fn by Fs. That will be negative because from this expression we can see that Fn is greater than Fs, because when we multiply Xc by Xt under root Xc by Xt, obviously it will give a value of greater than Fs. So therefore S will become negative. So when the sleep will become negative, what is the condition? This condition is similar to the induction motor running at super synchronous speed. That is nothing but it will work as the induction generator with having the negative slip, right? We will see the equivalent circuit under the faulted condition. We can see here the equivalent circuit where we are neglecting the shunt inductances and the coreless component of the resistance. So approximate equivalent circuit of the synchronous generator with sub-synchronous frequency starter current will look like this. So the magnetizing and coreless component branch is ignored in this case. The R effective is the summation of transmission line resistance, starter resistance, and the rotor resistance referred to the starter. Okay. And similarly, X effective is the summation of the transmission line reactance, starter leakage reactance, and the rotor leakage reactance referred to the starter. Since the slip is negative, the variable rotor resistance becomes negative, leading to self-excitation in the circuit. So this rotor resistance is becoming negative because of the negative slip, and that will lead to the self-excitation in the circuit, and the oscillation will keep on increasing, reaching unacceptable level. So this causes this when this interacts with the rotor or the shaft. So this gives, we call it torsional oscillation. So we are not covering detail of this study. So this is a kind of research topic. So we are not going very deep inside this torsional oscillation. Okay. So next, up to this is your small signal stability analysis is finished. So now we'll talk about the transient stability analysis. So this transient stability analysis we have discussed little bit in the beginning when we started our class. Already we know the definition. What is transient stability? It is the ability of the system to stay in synchronism when subjected to large disturbance. Okay. As compared to the small signal stability, it is the large disturbance. Because of the large disturbance, it happens. So due to large disturbances like faults, large load variation, generator outages, etc., there will be large swings in the electrical power outputs, rotor angles, rotor speeds, and bus voltages of the generators in the system, right? So this is because of the fault, large load variation, generator outages, right, etc. Due to this region, the power system cannot be linearized, like in case of small signal stability analysis. The system cannot be linearized for large disturbances, hence eigenvalue analysis cannot be used for assessing the stability as the system of the equation is nonlinear. The one way of assessing the effect of large disturbances on the system stability is through numerical solution. Already we did this in your beginning classes, considering the numerical integration method. So here we'll see the detail how we can do the numerical solution for a differential algebraic equation, the system represented by differential algebraic equations. The time of interest for the transient stability assessment is typically 2 to 10 seconds. So after a disturbance, the analysis period is 2 to 10 seconds. So therefore, during this time, usually it is assumed that the turbine and the turbine governors will not be acting as they are the mechanical system, as they have the slow response. So therefore, we are not considering the analysis or considering the model of turbine and the governor system. We'll assume that turbine is having the constant mechanical torque, that is Tm, which is sufficient for this type of analysis, which is in the range of 2 to 10 seconds. Hence, for transient stability analysis, usually the turbine and speed governor dynamics are not considered, and the input mechanical torque Tm is considered constant. Okay, so we'll see now the numerical solution of differential algebraic equation. The differential algebraic equations are already derived, and we have already derived and seen the model of the whole system, like considering the model of the synchronous generator in the network, then other devices, and it can be solved through the numerical methods. There are two methods by which the differential algebraic equation can be solved. There, one is known as simultaneous method, and other one is your partitioned method. So what is simultaneous method? In simultaneous method, both the differential and algebraic equations are solved together in each iteration. Whereas in partition method, first the differential equations are solved. So first step is to solve the differential equation, and then in the second step we solve the algebraic equations. So this has two steps. The partition method has two steps. First step is to solve the differential equation. Second step is to solve the algebraic equation. Whereas in case of simultaneous method, it solves simultaneously the differential equation and the algebraic equation. The simultaneous method is numerically stable. That is, the error will not accumulate over the iterations. So it will not accumulate in each iterations. It will be removed, leading to the blowing off of the error and making the method unstable. Okay. So in case of simultaneous method, the error is gradually removed in each iteration, but in case of partition method, it is accumulated over all the iterations. Though the method is stable and computational complexity is much more as compared to the partition method. It is simple, but the computational complexity is more in case of simultaneous method. Partition method is numerically unstable. That is, if the time step of the integration is not chosen properly, the error will accumulate over the iterations, leading to the numerical instability. Okay, this is the drawback of the partition method. We have to choose very correctly the integration steps. If it is not chosen properly, then the error will accumulate over the iterations. But the partition method is computationally simple as compared to the simultaneous method. The time step of the integration depends on the system steepness. That is the ratio of the highest to lowest time constant in the system, or the highest to lowest eigenvalue of the linearized system. So time step is chosen according to the system steepness. The time step of the integration in a partition method should be less than the lowest time constant, else it will lead to numerical instability. Okay, so in case of partition method, we choose the time step that is less than the lowest time constant in the system. In case of simultaneous method, even if the time step is greater than the lowest time constant, numerically it is stable, but the dynamics corresponding to that time constant are not visible in the solution. Let us consider one by one. First, we'll see the simultaneous method. It is also known as implicit method. So, generally in the literature, it is known as simultaneous implicit method. The differential equations already derived, we can express in this form. That is x dot equal to x f of as a function of x, I dq is the current, the dq current, and v is the terminal voltage, and u is the input variable. X is the state variable. So your state equation as a nonlinear function of state variable and other variables can be represented like this. So where your x is your state vector, which is consisting of x1 to xng. Ng is nothing but the number of generators, and u is the input vector matrix, which is u1 to un. No, it is not un, it is ung in fact. Okay, ung, and I dq is the dq current, id and iq both, that is for the generator, for ng number of generators, right? If we expand this, we can see one state vector, that is, let us say ith state vector, can be written in this term: delta I omega I psi 1d psi 2q eq dash ed dash efd vr and rf. Okay, vr is the regulator voltage and rf is the rate feedback. So here we can see there are 9 state variables, but in case of small signal stability, we have seen there are 14 state variables. Here it is reduced because of there is no consideration of the turbine and the governor. So therefore 5 state variables reduced. Ui is the input vector, that is V reference and TMI. So this is for also for all the all the generators, and similarly IDQ, the parameter which is for all generators, and this voltage, which is the voltage representing the terminal voltage or the bus voltages. So this will be for all the buses. That is, therefore it is mentioned N, right? So now your state equation is represented as x dot equal to f of x idq v bar u. So this state equation, so how will represent the algebraic equation? What are the algebraic equation we have? That is the network equation. So we can write here. One more assumption is considered here. If the salience is neglected, then xq double dash will be xt double dash. Then the generator current can be written as this. Okay. This is one of the algebraic equation we can say. So the generator current can be written like this. So I can write this equation in the form of a function h. So I can write idq equal to h of x b bar. X is the state variable. So here we have the state variables and the vi. So both are there. Similarly, the algebraic equations can be written as, for the network equations, algebraic equation for network, we can write this above two equations are for generator buses and below two equations are for load buses. So this is there for from I equal to 1 to ng, and below two equations are from ng plus 1 to n. So this is the real power equation for load. This is for real power equation for generator bus. Reactive power equation for generator bus. Reactive power equation for load bus. This pi and qi nothing but they are the real power and reactive power injections at the generator buses, and these are the equations for the power injections in terms of the voltage and bus impedance, bus admittance matrix elements. Similarly, for the load buses, we have written here the equation real power injection and reactive power injection. Then your okay. In fact, this will be minus PL. Okay, is minus PL and minus QL. You can see this will be PL minus. It is written PL minus this equation, so it will be minus PL minus QL equal to 0. Okay. So now it has to be noted that solving these equations is nothing but solving the load flow equation. So solving the load flow equations, what method we use? Generally Gauss-Seidel or Newton-Raphson method we use. So here also we'll use the Newton-Raphson method. We can see as we go ahead. So these two equations can be expressed as nonlinear function, and it can be shown as this: g of x idqv equal to 0. Okay, so now previously we have one equation, that is state equation. Then we have algebraic equation, which is one equation is here and other equation is this one, this equation. So we have algebraic equation and state equation. So combinedly we can write this is your system, whole system equation. That means these equations represent your system. Okay, that is the one state equation and two algebraic equation. Now we need to solve these three equations either through implicit method or explicit method. That is the simultaneous method, or you can say partition method. So the nonlinear differential equation can be numerically integrated through trapezoidal method. Generally, we know this trapezoidal method. That is, we will solve this nonlinear differential equation xn plus 1 equal to xn plus integration of tn to tn plus 1. So tn is the time step, f of x, that is the function, given nonlinear function with respect to dt. So we can write this above equation as xn plus 1 equal to xn plus delta t by 2 multiplied with the functions evaluated at time step n plus 1 and n. So here it is the function evaluated at n plus 1. This function is evaluated at n, which is summed and divided by 2. and multiplied with the times or integration step, that is the integration time step, that is delta t. And when we add it with xn, that will give us the new xn plus 1. This is the trapezoidal method to solve the differential equation, nonlinear differential equation. So where delta t is nothing but Tn plus 1 minus Tn. The n plus 1 instant algebraic equations can be written as this. At n plus 1 instant, we can write the algebraic equation in this. So now we have these three equations. This equation we obtained from your trapezoidal method, and there are two algebraic equations. So we have now three equations which we need to solve. How can we solve? We can solve using the Newton-Raphson method. Okay. So let the above equations be represented in terms of the three nonlinear functions f1, f2, f3. We can represent this equation as f1, this as f2, this as f3. So now these three equations we have. So now these three equations can be solved together using the Newton-Raphson method. Okay. So these equations can be solved by Newton-Raphson method, where variables are xn plus 1, I dq n plus 1, and vn plus 1, and un plus 1 with. So we'll consider here the initial conditions as xn, I dq n, vn, and un. So these are the initial conditions. Considering this, we can solve using the Newton-Raphson method. So since the variables at nth integration step are not explicitly required for finding the solution of the above equation, hence this method is also called simultaneous implicit method. Okay. The Jacobian of the Newton-Raphson method at kth iteration at nth integration step can be given as. So if we'll apply the Newton-Raphson method, we need to evaluate the Jacobian. So the Jacobian at the kth iteration, how we'll find? This is the equation. This is 0 minus f1, f2, f3 at kth iteration. The functions are evaluated at kth iteration equal to Jacobian matrix at kth iteration, and delta xn plus 1, delta idq1 plus 1, delta v bar n plus 1. So this is your error vector. This is your mismatch vector. So we need, so this is known, mismatch vector is known, and Jacobian is also known. From the initial condition we can calculate it. So only we need to find this error vector, which will be added to the previous value to give the new value, right? So therefore this is your error vector at kth iteration. Now the new value for the next iteration we'll find it will give delta. So no, sorry, this is your error vector. Error vector will be minus j of k, that is Jacobian inverse, minus f1, f2, f3 k. So this is your error vector. Now error vector will be added to the previous iteration values. This is your previous iteration value. This is your error vector in the kth iteration, which is added together. That will give us the new value, that is at the k plus 1 iteration, variable values, right? Then this is the value at k plus 1 iteration. So then how to check the convergence? Already we know in the Newton-Raphson method, we have to find the error vector and we have to check the convergence, right? But each nth integration step, the Newton-Raphson method is applied to solve the equations and are iteratively repeated at each integration step. So this is the complexity. So at each iteration step, at each integration step, we have to iteratively find the solution using the Newton-Raphson method. Okay. This is the convergence checking, how to check, how to stop the iteration at a particular integration step by checking this convergence error, right? where epsilon is the error at kth Newton-Raphson iteration in nth integration step, and it depends on the accuracy required. In very dishonest Newton-Raphson method, the Jacobian is kept constant for several iterations and also for several time steps. Except at the time of system disturbance, the Jacobian is considered to be constant. So unless the system is disturbed, the Jacobian is considered to be constant. Let's consider then the partitioned or explicit method. So in partitioned explicit method, first the differential equations are numerically integrated at nth integration step, and then the algebraic equations are solved. This has two steps. First step is to solve the differential equation using some numerical integration method, like we have also previously discussed, like Euler's method, modified Euler's method, right? There are several other methods as well, Runge-Kutta method, right? So the numerical integration can be done by different methods. Like here we'll discuss Euler method, modified Euler, Runge-Kutta. Okay. Euler's method we have studied, right? In Euler's method, the integration, this is your system equation. This is a nonlinear differential algebraic equation, which will be solved using the numerical method. Then the algebraic equations are solved using the Newton-Raphson method, right? Okay. So Euler's method, the integration of the differential equation at nth integration step can be given as this. This is the equation through which it gives the integration method of using the Euler's method, right? That is xn plus 1 is equal to xn plus delta t by 2. Delta t is the time step. A function is xn idq bn bar un. Okay. Where delta t integration time step and should be less than the least time constant of the system in order to have a stable numerical method. Once the variable xn plus 1 at nth integration steps are found, then the algebraic equations can be solved by solving the equations. So once we found this xn plus 1 at nth integration step, then we can solve the algebraic equations by using the Newton-Raphson method. Okay. And similarly, modified Euler's method, already we discussed this as well. The modified Euler's method, first we need to find the predictor variable, predictor step, and the predictor integration step, and then corrector integration step. So in the predictor step, we first find the xn plus 1p directly by adding delta t by 2 function evaluated at nth integration step with xn, and then after finding out the variables at the predictor integration step, we have to then solve the algebraic equations using this predicted value or predictor step variables, right? Then after solving the algebraic equations, then we go for the corrector step. In the corrector step, again we find the variables xn plus 1c. Then again we solve the algebraic equations with the corrected values, right? Corrected variables. So therefore there's two steps. First step is first we find the predicted value. Then using the predicted value we find we solve the algebraic equations. Then considering all the variables, we go for the corrector step. The corrector step, after finding the corrected value, we again solve the algebraic equations using the corrected values, correct variables, right? Okay. So this is how we solve the using modified Euler's method. This is your partition method. And similarly, Runge-Kutta method can also be used. Here, Runge-Kutta fourth order method is used. In Runge-Kutta fourth order method, the integration at nth step is given as this. This is the equation by which we solve nonlinear differential equations using the Runge-Kutta method, that is xn plus delta t by 6 multiplied to k1 plus 2k2 plus 2k3 plus k4. What are the k1, k2, k3 and k4? Let us see. Where k1 is function evaluated at the previous variable values, and then we find the xn plus 1 equal to xn plus delta t by 2 into k1. Then using this xn plus 1 we evaluate k2, that is function f function evaluated at xn plus 1. Then again we find xn plus 2, which is used to evaluate k3. Okay, so then similarly xn plus 3 is evaluated by writing xn plus k3 only here. Okay, and xn plus 3 is calculated here using this. So here we missed, I think it is delta t by 2, k3 into delta t by 2. It is missed. You can note it. So k4 similarly found. So these k1, k2, k3, k4, they indicate the slopes. In fact, right? They are the slopes at the beginning and two middle points and at the end. Okay, these are the four slopes, and they are used to find the new variables at new integration step. Euler modified Euler and Runge-Kutta are also called as explicit methods because the variable xn should be known to compute xn plus 1, whereas in implicit method it is not required. Okay, so this is how we do the transient stability analysis. So already we covered the implicit method. So next class we may discuss little bit more about the transient stability. Then we'll finish this transient stability part. Okay, so we'll stop here. So thank you very much. If you have any question or any doubt. Hello.
Hello, sir.
Yes.
So how we will calculate the lowest time constant?
Lowest time constant.
Sir.
It will be depending upon the various devices, various equipments we are using, right? Like generator. For generator, we calculate the time constant, right? And also in case of exciter circuit, we have a time constant. In case of the transmission line, we have a time constant, right? So we can calculate using the L and R values. You can find the time constant. Okay.
It will be a fixed value, no, sir. That why it is written only that lowest time constant.
It is not fixed for the whole system, right? It is for various devices. It is various different. Like for transmission line, it is different. For exciter, it is different. For generator, it is different, right?
Yes, sir.
For generator starter circuit is different. So time constant for different system, it is different.
Yes, sir.
So the lowest of that will be considered.
Yes, sir.
Okay.
Yes, sir.
So any other question? Everybody is present?
Yes, sir.
Yeah? I think Ashwini is not present, right? Hello? Okay then. So we'll then stop here. I'm closing. Okay.
Okay, sir.
Okay. Thank you very much.